just to recap a little bit, on Monday I briefly reviewed on the basics of black hole perturbation theory, trying to give a slightly different perspective, showing you how to derive the equations in generic dimensions. And then we briefly sketched the derivation of the main equations that describe the perturbations around black holes, which are the Regge-Wheeler, the real equations, and the Teokovsky equation for rotating black holes in general relativity. And we quite quickly discussed about some symmetries, some of the physical properties that we expect from these equations. So today we are going to see how to solve the equations and what are in fact the aspects that in the end we measure when we observe gravitational waves, in particular the ring down of the coalescence process of compact objects after the merge. Okay, so I will start from here unless there are some questions about last time. Of course, some notes have been sent. If you see any typos or mistakes, let me know. So it's pretty likely that there are typos. So if you see something, just stop me and we can check. We can fix it. Okay, let's start from Poisson modes. So before talking about Poisson modes, let me briefly recap what is pretty obvious, but what the normal mode is. Well, we are all familiar with normal mode analysis. So if we take, let's say, a finite system, we usually try to solve. There is maybe an ordinary differential equation or a system of ODEs, and we usually impose some boundary conditions, for instance, the vanishing of the wave function at the boundaries of the finite system, and the outcome is essentially some set of frequencies, which we call a normal mode. The simplest example, if you want, is the case in which we have a one-dimensional string with fixed ends. So if you call with, I don't know, L, the length, rho, the density, and T, the tension, okay? And the propagation in the string is described, of course, by a wave equation, which is, you know what it is. Okay? And v is the velocity, which is t over rho, squared is t over rho, and we impose, for instance, the Schrey boundary conditions in which psi of 0 L is equal to 0, okay? And we know that there is a solution in the form of which is
Bonjour à toutes et tous. Ceci est un message destiné aux électeurs de
So we're saying that we have, you know what the solution is, and this psi n, as you know very well, these are just the sine of omega n x over v, where omega n are just phi n over L to t over rho. Okay, so where these omega n are real numbers, while n these are integer numbers. Okay, so we have a discrete spectrum with this frequency. This is what we typically have in normal mode analysis. Okay, so this is pretty obvious. So just as a warm up. Of course, now perturbations of a compact object or a black hole, if you want, are slightly different in the sense that, first of all, perturbations can escape to infinity. So in this sense, the system is more similar to an open system rather than a finite string, if you want. And we will see that, in fact, but differently, let's say, from if you take an open system and you study scattering of some potential, in which maybe you send a wave and you're interested in computing the transmission reflected probabilities for quasi-normal modes, as we will see, the boundary conditions are slightly different. Okay, and in fact, the frequencies are not real, but will be complex. So what I mean is the following. So let's go back to the potential that we have drawn on Monday. So if you, for instance, if you take a non-rotating black hole, and so we have written down the Regge-Wheeler and Zerilli equations. We said that there is some sort of potential. There is a potential, which is the Regge-Wheeler-Zerilli potential, which is a function of R. Okay. And if we write this potential as a function of R star, minus infinity is the horizon, plus infinity is where the observer is, if you want. So typically in scattering problems, for instance, in quantum mechanics, we say, well, let's send a wave, and we are interested in computing the reflected and transmitted waves. Okay, so reflected and transmitted probabilities. This problem. This is not quite the boundary conditions that we are interested in. In fact, for quasi-normal modes, for a compact object, let's say that we have a perturbed black hole, there is no incoming wave. Okay, so the boundary conditions that we impose are purely outgoing waves. Okay, this is the physical system that we are interested in. This is the boundary value problem that we are going to impose when we solve the Regge-Wheeler and Zerilli equations. Of course, this is not the only possibility. If you are interested, let's say, in considering the accretion of some matter or dark matter for a black hole inside some external environment, of course, you will have some incoming flux. But let's say that we take an isolated black hole and we want to solve the problem given these outgoing boundary conditions. Okay, so this is the setup. But in practice, what we will impose is that if we have the capital psi, which is either, if you want, the Regge-Wheeler or Zerilli field, as R star goes to plus infinity, this has to go like into the minus omega minus R star. Okay. And similarly, if you go to the horizon, we are going to require that this goes like, sorry, this is a nice here, minus I omega t plus R star. Okay. So these are the boundary conditions that we solve. We have a second order ODE, and we have to impose two boundary conditions. So everything is fully fixed now. So let's solve the equations. Yes.
But during the spiral, it's okay to keep each black hole like isolated with no ingoing mode.
Well, here we are talking about the final stage of the merger. In other words, the two objects merged. Now you have a single object which is perturbed. So we are solving the problem of an isolated object which is perturbed and which is relaxing to the equilibrium configuration. Of course, if there is some extra environment, this has to be taken into account, and there will be some modifications, some effect. Okay. Okay, so let's try to see how to solve this problem. Erase these that we think we all know what it is. Don't need. So in fact, so let's construct, let's study, if you want, let's construct, let's provide the solution to the problem in a constructive way. In fact, so in other words, let's actually put a perturbation. So now, instead of taking the Regge-Wheeler and Zerilli equations without a source, let's put a source, and let's try to see how to solve the problem. So in other words, let's construct the Green's functions associated with this equation. So for instance, what I mean is the following. Let's rewrite the Regge-Wheeler and Zerilli equations. Let me use x instead of r star. So here x is going to be essentially r star. Just because I'm a bit lazy, so I don't want to write two symbols. I'm just one. So let's call it x, okay, plus b psi equals 0, okay. Now instead of 0, we put a source, the function of t and x, okay. In fact, it's a one-dimensional problem, so there is this is really 1 plus 1, okay. And so we know what the solution to this problem is. In the end, the solution is given by this. So we d prime, dx prime, we have some Green's function, dx prime, x prime, and convoluted with the source. Okay. So of course, the source, in other words, if you want, is given, and the whole problem is about computing the Green's function, and the Green's function, as you know very well, satisfy the same equations. Okay, and of course we require that the boundary condition for the Green's function is that the g has to be equal to 0 for t less than t prime. Okay, so this is the standard notion of classical causality, or a primitive notion of causality, so just retardation. Okay. Now it's convenient, so we will assume also that this J, the source, so the initial data, for simplicity, let's assume that has compact support, or at least is very sufficiently localized. We can then, it's convenient to introduce the Laplace transform. So the Laplace transform, let me remind you what the Laplace transform is. So it's just integral 0 infinity in t minus xt g x prime. Okay, and then introducing the Laplace transform, the equation for the Green's function is something like this. So there is some operator acting on the Green's function, which is essentially minus dx d2x plus s squared plus the potential acting on the v. Okay, equal to delta function. Okay. Of course, we can take there is the in direct space, if you want, the Green's function can be obtained by inverting the Laplace transform of G, which is essentially something like this. It's an integral between c minus I infinity, c infinity of s to pi I, and s prime of G. Okay, so this is the standard inverse Laplace transform. This c is a positive real number. In the end, the result is independent of this c because of holomorphy of G. In other words, we're just integrating along the instead of the imaginary axis, we are translating it into bit in such a way that all poles of the Green's functions lie on the left side. Okay, and we are going to ask that this G, if you want, is bounded in such a way that is required, so is bounded for the real part of S positive, okay, in such a way that we can close the contour from the right, and the analyticity tells us that in fact this boundary condition is satisfied. So if t is less than t prime, this is negative, I can close the contour to the right, and essentially by and this condition is going to be satisfied. Okay.
When is the Laplace transform useful? Can you remind
Here,
here.
for instance, or in problems where you have this type of problem, I would say. But you can also use the Fourier transform if you like. But
When you say this types of problems, do you mean when you have a Green function or when you have a quasi-normal mode?
No, when you have a Green's function. So for the moment there is no
Yeah.
So this is very general. So you take a generic 1 + 1 equation. This is so this is extremely general. So okay, maybe this might be useful later. So okay. So let's give, if you want, a constructive procedure for to obtain this Green's function G. Okay, and of course this is going to be pretty obvious, so you know how to solve it. For x that is different from x prime, essentially the Green's function satisfies this equation. Okay, so we can express G as in terms of homogeneous solution to the original equations, okay, and boundedness of G for real part of F positive, if you want, requires that G as x prime essentially is proportional to let's call it psi minus x, okay, for x larger than x prime. I will tell you what this psi minus is. Instead, this is proportional to another solution, psi plus as x for x less than x prime. What are these psi minus and psi plus? Those are the two solutions. Psi minus s such that when I send x to minus infinity, psi minus goes to e to the minus plus x minus, exactly, minus, okay? So the other way around. Let me do it carefully. So psi plus for x that goes to minus infinity, here plus, okay? Okay. Instead, psi minus for s x that goes to plus infinity goes to e to the minus s. Okay? In such a way that, as we said before, if this is the case, then we can send, for instance, if x goes to plus infinity, this goes like e to the minus x sx. So for the real part of s positive, this is bounded, and the same for the other direction. Okay. Now we know to proceed. Of course, we can write down the general solution. We are just going to impose, of course, this is true for x different from x prime, so we just have to impose some continuity, some matching conditions at x equals x prime. So first, let's write this Green's function. The Green's function, there will be some function of x prime, and then we are going to impose some continuity. So it has to have the following form. Yes, let me do it carefully. Psi minus x, for we have a theta function, x minus x prime, okay? And then we are going to have a plus psi minus s x prime, psi plus s x, and the other function. Okay? This is by continuity at x equal x prime, and now, of course, we can fix this function here by, if you want, you can integrate the original equation and impose a jump condition, if you want. So, essentially, in the end, what you're going to have is that limit epsilon to 0 minus x s x prime computed as x equals epsilon plus x g s x prime at x equal x prime minus epsilon is equal to 1. Okay. And now we are going to fix this 1 over ax prime, as usual, like minus psi plus s x prime psi minus prime, let me write it explicitly, x prime psi minus x prime minus prime x prime plus okay, which is just, you can recognize it, this is nothing but the Wronskian. Let me write below. This is just, you recognize it that this is just the Wronskian between two solutions, psi plus and psi minus, which is a function of S. Okay? And,
sorry, but this condition on G, on the derivative of G, where it comes from?
well, just you have the equation, you can integrate the equation. Okay.
Okay.
You get a condition from in a neighborhood of x prime, let's say. On the right hand side, you have a delta function, so you get the 1.
Ah, the one is the delta. Okay.
This is just the Wronskian. So as you know, the Wronskian is conserved, so it's a function of s only. It's not a function of x prime. So it's a constant. Right? Okay, so in the end, if you put everything together, we find that the Green's function in the Laplace transform of the Green's function is just 1 over the Wronskian. Again, let me stress that this is a function of S. Then we have psi plus S x prime minus Sx. We have the theta function x minus x prime, and then we have the plus s x prime, the plus x, and then we have the other function. Okay. So, and as we said, the x of w is equal to 0. So, in the end, you see that we are interested in understanding the analytic properties of the Green's function. This is what, in the end, will give us these quasi-normal modes. And let's start, let's say, by focusing on the poles of the Green's function, so the roots of this Wronskian. Okay. there will be some values of S for which the Wronskian is 0. So let's consider the values of S for which W of S is equal to 0. Okay. Notice that when this happens, we are going to have essentially the Wronskian vanishes whenever psi minus is proportional to psi plus. Okay. What does it mean? This means that, in fact, the solution is such that it simultaneously satisfies the correct boundary conditions. Remember that psi plus and psi minus are the two independent solutions that satisfy the outgoing boundary condition. So when these two solutions are in fact the same solution, so this happens only for very specific values of S, we have a solution that satisfies the boundary condition that we imposed at the beginning. So these are precisely the quasi-normal modes. Okay? In other words, the quasi-normal modes are the values of S for which the Wronskian vanishes. Okay? And as you can imagine, they, of course, as I said, this does not happen for any S, but only for very specific values, and these values are in fact complex, and the quasi-normal modes come, if you want, in complex conjugate pairs, which means that if you have a solution for psi with some S quasi-normal mode as a function of X, you will also have something like this. You will also have psi star, so this goes to solution, quasi-normal mode. So in other words, they come in complex conjugate pair. Okay. The question was this obvious? Shall I go faster, slower? We have comments. So let's put everything together now. So if I put everything together, the solution in real space is going to be something like this. So it's an integral in prime dx prime. Then we have the integral c minus I infinity c plus I infinity of ds over 2 pi I ds t minus prime gs t gs x prime of the source prime x prime, and if we integrate in dt prime, we are going to get an integral in dx prime, an integral in infinity ds by I st. Then we have gs x prime, and then we have the Laplace transform of the thing. Okay. But this is just algebra, so I'm doing something very trivial if you want. So why is this useful? For the following reason: if imagine that the Green's function here has only poles, if this were the case, now what you do to compute this integral in ds, well, you just close the contour on the left where these poles are, okay? And what you're going to find is something like this, psi tx. Let me put a question mark here because we don't know if there are only poles. So, but imagine that there are only poles. What you find, well, using the residue theorem, you will find that this is a sum of e to the s qt, okay? And then you have the residues where the Wronskian vanishes, basically. Let me write in this way, okay? So it's clear what I mean. So you just have to compute the residue of all these poles on the left of this line, okay? Because you are closing the contour. You have this line, and then you are closing the contour on the left, and these there are poles here. Imagine that there are only poles, okay? And then, of course, here you get minus SQ x, and then you have the integral from minus infinity to x dx prime plus SQ x prime, and then you have the source SQ x prime. Okay, I'm just doing the trivial algebra. I'm just substituting and computing the integral. Minus psi plus of SQX, and then you have the other integral from x to plus infinity dx prime, and then minus, and then prime j of x prime. Okay? So again, if there were only poles, this is the result that you would get. And if you assume that, for instance, just to give well, some better intuition of what's going on. So if you assume that this J has compact support, let's say that JS and X is non-zero for so let me call it yes, X prime for X prime only in a compact interval. Okay, imagine that this is the case. Then you would find that essentially psi px is just going to be, let me put again the question mark, the sum over q, some coefficients e to the I sq t, psi minus sq x, where these coefficients, we know what these coefficients are. These are just the derivative of the Wronskian, and then you have the integral between x1 and x2 on the compact dx prime of psi plus sq x prime times the source. Okay? So I'm writing this to emphasize the following. So if this were the case, then the problem would be very, very similar to the case of the finite string. You remember the finite string, essentially the result is this one, with the only difference that in that case the frequency was real, while in this case S is complex. So if there were only poles, this would be the result. So you see that there are some similarities, but there are differences, and there are important differences. The first one, I already mentioned the first one, which is the fact that these frequencies here are complex. Okay, you don't have oscillations, but these modes in fact decay. And that's the reason why they're called quasi-normal modes instead of normal modes. And in addition, the notion of completeness cannot be directly translated into this context. In fact, another difference is the fact that now, if I go to real space, you remember that the solution is going to be something like this: minus e to the minus I omega t, let's say minus x star, far away from the potential. That let's say that it has compact support. So outside the potential, this guy is going to decay in time, but it's going to blow up in R. Okay. So, and this is another important difference. Another one is that there are not only poles. So if you study the properties of the solutions, if you study, I think I erased it. No, so if you study the properties, the analytic properties of these psi plus and psi minus, you discover that there are not only poles. There is also a branch cut. In other words, the picture is more like the following. So you have so there is a branch cut here in this region. So this is the complex plane for S. So this is the imaginary part of S, and this is the real part of S. There is a branch cut here, and in fact, instead the poles lie like here, if you want. And this is the integral that we are kind of computing. So we are taking the compute here, and then we go around. So this is kind of the compute that we are computing. But there are not only poles. There is also a branch cut, which is essentially due to the fact that, if you want, in the end, remember that the potential is such that it goes like 1 over x squared at large distances from the black hole. So it decays like 1 over x squared, and so it doesn't decay exponentially, and that's that's, if you want, the main reason why you have a branch cut. Okay? So this tail is yeah, if you want, this tail becomes dominant after the phase in which you can describe the signal with the quasi-normal modes. In other words, quasi-normal modes are a good description of the ring down, if you wish, for before this tail takes over. Okay. And then there is also another difference, because there is a contribution in principle also from these arcs infinity, coming from the fact that you have some, let's say, it is associated to high frequency signals that are completely insensitive to the presence of the potential, and that so these are, in some sense, the ways that propagate on flat space.
Sorry. About the quasi-normal modes, are they in infinite number? And if yes, where do they? But they could accumulate somewhere. Where do they go? They are sparse on the plane, or they have some asymptotic axis. I don't know.
Yeah, I think there is some asymptotic, if you want, and how should I say? Yeah, I think so. Part of this, so a subset of these modes can be understood analytically in certain limits. For instance, the high frequency or so the economic limit. So you can understand some asymptotics if you take some limits.
Because there you wrote as if they were accumulating towards the imaginary S part or the real axis.
Well, because I'm not my skills in drawing are not good, but
Okay,
no, it's true. So in the end, so as we will see, these modes are computed numerically, unless you have some certain limits where you have some analytic understanding or some approximation. Yes.
So, contrary to what is on the picture, some of these pods, they have a real part of S which is positive. I mean, to the right of the branch cut. So, no, because if I look at this picture, I would assume that at late time, I would be dominated by the singularities which have the largest real part of S, no? Because of this exponential ST, no?
You're dominated by
negative with zero. In the end, probably there is some mechanism to bound the real part, no? So, there is due to the potential.
What do you mean mechanism to bound the real part?
Bound the real part. The fact that the real part extends up to the real part, the
Yes.
branch cut.
Yes.
What's the support of the branch cut?
Well, it goes from 0 to minus infinity. Because it has to be, the function has to be analytic on the right because of the causality or retardation. Is what you're asking, or maybe not? No.
No, because, more or less, because if the branch cut goes to 0, I mean, extends on all the negative real axis.
Yes.
I would expect that at late times, I would be dominated by the singularity at 0.
You will be dominated by the branch cut. Yes.
Yeah.
Yes.
Okay, that's what you said. I believe
Yes.
you said it. Yes, sorry.
No, I think that's correct. Yes.
Do you know, I mean, what's the structure of the B and your eigenvalue problem such that the imaginary part just pure point spectrum rather than
Yes, it is a discrete spectrum. Yes.
So it's pure point, but do you know what's the hypothesis you make there to have it? Or
Well, essentially what we said. So let's say that, of course, there is a question mark here, so there are subtleties, but let's say that you are interested in the poles.
but you are assuming that you have, I mean, if you have a continuous also.
No, this is an outcome because remember how these quasi-normal modes are computed. They are the poles, sorry, the zeros of the Wronskian. And the Wronskian is zero, not everywhere, but only in isolated points. So for special values of the frequency, if you want. So in the end, you get the discrete spectrum, which corresponds to the zeros of the Wronskian.
Sorry, just another one. So maybe one can see it simply, but can we prove that all the poles hide in Wronskian, or for example, if there is no some cancellation between poles in the Wronskian and factors of S from independent solutions or something like this, is this possible?
Well, let's see. So, but how can you get cancellation for all values of x? Remember that, of course, so there are special points, like to say, which so there are special modes. Maybe we can come back to this point later, which is related to the discussion of, that we had on Monday about this Darboux transformation. So there are some special points, but let's say that in general, as a criterion, what we found is that we are going to require. So remember that in order for this to happen, in order to be able to enforce that the solution that we have satisfies both of going boundary conditions at the same time, this requires the Wronskian to vanish. So the Wronskian is only a function of S, and the vanishing of the Wronskian, of course, does not happen everywhere. So for all values of the frequency, but only on very special points. Okay, so let's so if you want, let's recap a little bit. So well, we already did, but just to stress. So in the end, what you find is that the solution is a sum over some something like this, so which is very similar to the normal mode problem. Okay, except that there are some other contributions here. So let's call it other contributions. Okay? And these other contributions come from out of three types, if you want. The first one is, well, so in other words, the solution contains three ingredients. The first one is the quasi-normal modes that we discussed, which can be associated precisely with these values where the Wronskian vanishes. Then there is the branch cut. And then there is the contribution coming from, so the branch cut, as we said, is subdominant for intermediate values of times, where in fact the contribution of the quasi-normal modes is more important. And then, if you want, there is the flat piece of the Green's function. Okay, and in the end, these frequencies. Now let me go to let me call it omega. Is labeled by three numbers in general. There is a number n, which is called the overtone. Then there is L and M in general. So you know what L and M are. L and M are, of course, the quantum numbers of the spherical or spheroidal harmonics that we wrote the other day. So, of course, for For Schwarzschild, there will be no dependence on M because of spherical symmetry, but for Kerr, there will be also dependent on M. So in general, this is the result. We have a discrete spectrum of frequencies labeled by 3 numbers. Okay. So toward the end, we'll try to comment also on, let's see how far we can go, but to comment also on some recent results about nonlinear quasi-normal modes, where this story is changed, how this story changes if you take into account nonlinearities in GR. Okay? But for the moment, in linear perturbation theory, this is more or less the picture.
Sorry, just to understand, omega is SQ.
Omega is S, yes.
SQ, okay.
With
the other
the standard Fourier transform instead
okay.
of. So I don't know. Let's see. If you want, we can consider a simple example. At least to give an idea. It's not that it's particularly instructive, but at least gives an idea of how so an application of this logic. So a simple example is something like this. So let's consider this equation. Let's consider a toy model in which you have, let's say that we modify the Regge-Wheeler and the real equation introducing some Postel-like potential. Alpha at star minus star bar. Okay. Where at star bar is the value corresponding to the maximum of the potential. Okay. V0 is the value of the potential at the maximum. Okay. And alpha is defined as if you want, the curvature at the maximum. Okay. Now you can do some algebra. For instance, it's convenient to introduce some psi, which is the -2 alpha at star minus alpha bar, the -1, and then you can also introduce. We do a field redefinition in this way. Minus I omega to alpha is phi, and you discover in the end that the equation for this new field phi takes a simple hypergeometric form plus C minus A plus B plus 1. So, phi prime minus AB equals 0, where A, B, C are some parameters, so let me write them down, but it's not particularly illuminating. Alpha square minus 4B0 to omega, and then B is the same, but with a minus sign. So it's the same square root minus 2I omega, okay? And then C is some other parameter, I omega. Anyway, so this is just a toy model. So let me go quickly to the point that we want to make. You can find now the two independent solutions. So since it is an hypergeometric equation, we know everything about hypergeometric equations. So you can find that the two solutions are something like this. Omega to alpha minus I omega to alpha. And then we have the geometric equation A minus C plus 1, B minus C plus 1, psi. And then we have some B coefficient, psi 1 minus psi. And the geometric function A, B, C psi. Anyway, so the message is the following. We have two independent solutions. Of course, we have a second order ODE. These are the two independent solutions in terms of hypergeometric functions, okay, with some coefficients A and B. Okay. Now we are going to impose the outgoing boundary conditions that we said. So we want to see, how these quasi-normal modes come about, okay. And at special infinity, so when f star goes to plus infinity, which means also that psi goes to 1, okay? Okay, and instead, so 1 minus psi goes like to the minus 2 alpha x. Okay? Instead, at the horizon, it goes to minus infinity, psi goes to 0, and psi goes to e to the 2 alpha. Okay? So since this hypergeometric function in 0, in psi equals 0, is normalized to 1, and this guy here scales like e to the minus omega star. Let me write it. Psi 1 minus psi omega alpha scales like minus I omega star as psi goes to 0. This implies that in order to have the correct boundary condition, we need to impose that A is equal to 0. Okay? Because this is precisely the boundary condition that we want. Okay? Instead, this other guy is going to give us the opposite boundary condition. So instead of outgoing, it will be ingoing. Okay? So we are going to fix this boundary condition. And then we do some algebra. We do some algebra that I will not do. We find that psi goes to 1. So now let's consider infinity. Okay, we expand at infinity. The solution goes like d e to the I omega star times something that goes like the following: c minus a minus b times some gamma functions. A gamma b, c gamma c minus a minus b divided by c minus a gamma c minus b. Okay, this is just algebra. The message is the following. We want to impose also that at infinity the solution goes like so. Okay? In order for this to happen, we need this part to be 0. And this part is 0 either if 1 over gamma of A is equal to 0 or 1 over gamma B is equal to 0. So if this happens, then this part is 0. Okay? And if you impose this condition, then you find that in fact, so A, B, C are given here. You find that in fact there is a discrete spectrum. So you find some omega n. So there are some values of the frequency at which this happens. Okay? And the values of the frequencies are the following. 0 minus 1+10. Yeah. Anyway, the actual values are not super important. The reason why, so I wrote it is just to show you that what the logic is in practice. So if you have a certain potential, that's the logic. You impose the boundary condition or going boundary condition on both ends, and then you find the values of the frequency for which this acts. Okay, that's all there is. Of course, this is a toy model. The actual potential in physical situations is not this one. We cannot find a closed form expression, an analytic expression for these frequencies, and so we have to rely either on numerical methods or on some approximation. Okay. So let me tell you. Are there questions about this?
Do you have toy models with the
Solvable, you mean?
well, I don't know.
I don't have one in mind, I have to say, but maybe I'm sure that yeah, we can check on the literature. I don't have one in mind.
Okay.
Just here, I missed. What is the flat piece?
Well, it's the fact that if you want, there is so if you take a perturbation, there is a part, there is some propagation from the source directly to the observer that is completely, or a very high frequency regime, there is a part that is completely, that doesn't know anything about the existence of the potential. So it's like being in some flat space. So this part of the propagation is not particularly good. What I mean is that, so we can, if you want, this is pretty clear if you consider another a toy model. If you take, let's say, instead of this potential, you can take even a simpler one. Let's consider a delta function. Delta function is very, very part is written very, very explicitly. So in the example, you can completely solve for this gauge function, and then you can really identify the different contributions. Yeah. So just let me just say that stress that as we said there are of course in real situations you have to rely on some different methods. You cannot compute these frequencies in closed form analytically. So you have to rely either on numerical or so numerical methods if you want, or some approximations. And just to give some example, for instance, you can some exactly solvable case is if you go to the channel limit, or you can consider the case of a sort of a WKD approach. Or what is called the lever method. which is also sometimes called also continued fraction method, or you do some direct integration, or if you want a shooting method, or for instance, you do some time evolution, or uniform approximations, and so on and so forth. So there are so there are different methods. So there are different techniques that have been used in the literature to extract the quasi-normal modes, and yeah, some of these methods work better. Other methods work less well. For instance, the WKB approach, there are some, it is not particularly efficient. Let's say the liver method instead, or the uniform approximation, are more can extract the quasi-normal modes with higher precision. Of course, you have to have the explicit form of the potential, which UGR we know. So let me just say that so in some sense, as opposed to this scale that we talked about before, the quasi-normal modes, in fact, are mostly, there is a sense, let me say the following way, there is a sense in which the information about the quasi-normal modes is mostly contained in the form of the potential at the maximum, okay? And this appears clearly, if you want, in this WKB approach. That maybe it's, I can tell you a little bit about. Maybe it's a good time to have a break before, or if there are questions.
I have a question. Direct integration it means numerical direct. Okay, a time evolution also it's numerical. Okay.
And the Grenal limit, yeah.
Well, you take the limit in which L, the quantum number L, is very, very large, so the potential, you can drop some terms in the potential, so in such a way that it becomes exactly solvable. So as I said, there are various methods. We don't have time to maybe it's not going to be, it won't be very interesting there, but it depends what our interest. Of course, there will not have time to review all these methods. So let me just perhaps comment a little bit more on this sort of WKB approximation for again, not because it's particularly instructive, because it's a method that will allow you to compute the quasi-normal modes more very efficiently, but at least it gives an idea of why these modes are more sensitive. Let's say, at least there is a sense in which these modes are sensitive to the properties of the potential at the maximum. So let's start again with with a wave equation. Plus omega squared minus v, okay? Function of r upside to 0, okay? This can either be the Regge-Wheeler or the really potential. So let me, in fact, present this method in a way that is slightly different from the historical one. Well, at least in part. In the end, it's completely equivalent. But I don't know. Might be useful. So let me introduce some sort of Hamiltonian formulation of the problem. So it's convenient just for to help our intuition let's, instead of R star, let me introduce some tau. This will be some fictitious time coordinate, simply because we are more familiar with the Hamiltonians that depend on time. So let me introduce this Hamiltonian Q tau, which is essentially 1/2 squared plus 1/2 omega squared minus v minus v squared and yes, so P, you can check that if you compute, so Q dot is, as you know, the derivative Hamiltonian with respect to T, and then P dot is minus dH over dQ, yes, minus omega squared minus VQ, okay? And the equations now can be written as U over d tau T equals to 0, 1 minus omega squared plus V, 0, QP, okay? So this is just completely equivalent to the previous equation. Written
And v is the function of tau.
yes.
Okay.
And the boundary conditions for the quasi-normal modes now take the following form. Boundary conditions means that Q is essentially e to the I omega tau for tau going to plus infinity e to the minus I omega tau going to minus infinity. Okay? So this is completely equivalent to the previous problem, just rephrasing the problem in slightly different language. So if the potential goes to 0 sufficiently fast at large values of tau, it's convenient to perform, if you want, a canonical transformation that, if you want, diagonalizes the time evolution. So in other words, let's introduce these xi plus minus, which are 1 over root of 2 with omega q plus minus I q over root omega. Okay. Now the evolution equation becomes something like this. Equal to omega plus omega 0, 0 minus omega, okay, plus v of tau divided by 2 omega plus 1 minus 1 minus 1. Then you have psi plus and psi minus. Okay. Anyway, this is just a canonical transformation. I just redefined the P and Q, and this system is completely equivalent to this one. Of course, so we have now 2 first-order equations instead of one second-order equation, but it's completely equivalent. Okay. Now the boundary conditions in terms of this xi plus and xi minus are the following. So xi plus goes to 0, and xi minus goes to e to the I omega tau. Tau going to plus infinity, and instead that psi plus goes to the minus I omega tau, and psi minus goes to 0. Tau going to minus infinity. Okay, these are the boundary conditions, which are essentially completely equivalent to these ones. So, in other words, the boundary condition in this language, this is useful because in this language, what we're saying is that, well, if you start, think of the problem instead of, that's the reason why we introduced this fictitious time. So think of the problem in terms of some sort of time evolution. It's like saying that you start 30 times with a given, with a solution with the eigenvalue, which is a plus omega, okay, with a positive eigenvalue. And then you are going at late time, so you're going to switch to a configuration with the negative eigenvalue. Okay, so you need you have a sort of a transition. Okay, and if under the assumption that the potential is smooth enough, so the time evolution is adiabatic. The adiabatic theorem of quantum mechanics tells you that the transition can occur efficiently when the two eigenvalues become degenerate. Okay, what does it mean? Well, this means that let's compute the eigenvalues associated to this to the system. The two eigenvalues, let's call them lambda plus minus, are just plus minus omega squared minus v of tau. Okay? So, and we want these eigenvalues to become degenerate, but in fact, we want something more. We want that there is only a single level crossing. Okay? In other words, we want that the frequency omega squared is equal to the maximum of the potential. If the potential is the one that we have drawn before, okay, with the maximum, of course, if the frequency is like here, you will have two crossings. In order to have a single level crossing in such a way that, as we said, we have a transition between a plus infinity from a positive eigenvalue to negative eigenvalue, okay, under the assumption that the potential is smooth enough and the process adiabatic in this language of time evolution. This is the condition that you need to require. Which means that the frequency touches the maximum of the potential. By the way, this is also the condition that originally in the work by Choose-a-Will, let me spell it correctly. Okay. That's precisely the condition of this WKB approach. The language that I think they use is slightly different. They are requiring that, in other words, the amplitude. Remember that we want to impose outgoing boundary conditions. So the two outgoing waves better have the same amplitude. If for some reason the frequency is smaller than the maximum of the potential, inside the potential there will be some exponential damping. Okay, so the amplitudes will not have the same. The solution will, the boundaries will not have the same amplitude. Okay, there will be some damping. So this is the condition that you need to have in order to first the leading order if you want to compute the quasi-normal modes. Okay. So if you impose this condition, then the idea is, well, let me expand around the maximum of the potential. So we take the original equation, we go back to the original equation once we understood what the criterion should be. Okay. We expand around the maximum. So we Taylor expand around the maximum, so that we get by construction. Let me call the point where the maximum is a bar. Okay. Okay. And the maximum Vmax, as I said, is V star bar. Okay. But now this equation can be admits an exact solution in terms of parabolic cylinder functions. So in other words, we can write that psi as some coefficient times these functions labeled by nu plus v minus nu minus 1 I z. Let me tell you what this is 2 v double prime r star bar fourth e to the 5 4 r star minus r star. Okay, so this is just definition. Anyway, the message is that if you Taylor expander on the maximum, you can now solve in closed form the differential equation, okay? And nu, I can tell you what nu is. Nu is minus I omega squared minus V max divided by the square root of V double prime after bar, okay, minus 1/2. So now you can use the asymptotic expansion of these functions, so these special functions, okay, and they impose the correct boundary conditions, if you want. In order to have the correct boundary conditions at infinity and the infalling wave at the horizon, you have to have that 1 over gamma of nu is equal to 0. So this is some sort of Bohr-Sommerfeld, if you want, the quantization rule. This is kind of sort of resembles to some extent what we wrote before for the toy model. So you have some condition that reminds of that, and in fact, if you impose this condition, what you get is omega squared minus V max divided by root of 2V double prime after bar equal to I n plus 1/2. So this is the quantization rule in this approximation scheme. Okay. Of course, this is just an approximation. So this is what is called the leading order WKB approximation. Of course, you can do better. You can expand this at so leading orders and find corrections and so on. Okay. So, but the message is that well, this is just an example. As I said, this is not the best approach to solve for the quasi-normal modes, but this is an idea what are in which sense these quasi-normal modes depend on the properties of the potential. So in this sense, the leading order is dominated by the form of the potential at its maximum. Okay? Let me say that this method works very, very well in the aconal limit. So if you are interested in quasi-normal modes for large values of L, then this method works very well. In fact, the result becomes, there is a sense in which the result becomes exact. But it works very, very badly for large overtones. So very well when L is very large, but doesn't work when N becomes very large. Okay? So it's less and less accurate for large overtones. Okay. Questions for these? Of course, you can find the details about the solution methods, also numerical methods. There are reviews about these methods, so you can check. You can provide some reference. Okay, so unless you have questions, let me say something about nonlinear corrections to the quasi-normal spectrum. So far, the idea was to, well, at least I hope I gave you an idea of what these quasi-normal modes are, where they come from, and what are the various aspects that emerge when you try to compute these modes. Let me say something about nonlinearities. So, of course, we said that these perturbations decay exponentially. So it is reasonable to expect that linear perturbation theory, linear black hole perturbation theory, can give, can model, if you want, the ring down pretty reasonably well, if you want, for at a time, after a time that is roughly the time scale of the decay of these quasi-normal modes. Of course, if you get closer and closer to the merger, so remember that the signal that we have in mind is the following. So we have some spiral, then we have some merger, okay, and then there will be some exponential damage. So of course we are discussing this part. So this is the ring down that we are talking about. Okay, very schematically. Of course, as we said, there is a sense in which for the ring down, at least a part of the ring down can be very well modeled in terms of these exponentially damped oscillations. But of course, if we go closer and closer to the merger, at early times, of course, you expect this perturbation theory to break down. Okay? Because you enter a nonlinear regime where you need to take into account nonlinear correction to the Einstein equations. In fact, the derivation of these equations was done under the assumption that of a linear perturbation theory. Okay? So what do we do then? Well, the idea is to try to understand what happens if we try to expand the Einstein equations at quadratic order instead of stopping at linear order. So, and how do we do that? In fact, let me say just another comment. That could be, so why is this interesting? Why is this relevant? We said that linear modes are labeled by three numbers. So there is an overtone, there is L, and there is M. There could be, the question is, can there be nonlinear corrections that are perhaps, let's say, to linear correction to a fundamental mode, which is, I don't know, L equal to 2, M equal to 2, which is the one that is found to have the largest amplitude. Can there be numerical corrections, so nonlinear corrections to this mode that are in fact larger than overtones? Okay. So that's the question, and if the answer is yes, well, this means that eventually in the future, if you want to model the ring down precisely, you will need at least to take into account these nonlinear effects. Okay. So let's go back. Let's keep this in mind. But first, let's try to see how to extract at least the equation for these nonlinear corrections. The idea is that, as you can imagine, pretty straightforward. So again, let's go back to the basic. We take the metric, we expand around Schwarzschild. The G bar can be Schwarzschild, can be whatever solution you have in mind. And then at linear order, you have your these. Let me introduce some bookkeeping parameter epsilon. If you want, you can also think of epsilon as being the amplitude of these modes. And then we include the second order correct, okay? Times plus dot dot. Okay. Now we want to, as I said, let's take as a reference G bar is going to be let's take minus m of r squared plus d r squared r plus r squared square, okay, with the line element for partial where f of r is 1 minus r squared. Okay, just as a reference, let's take this. And then what we do is, well, we expand Einstein equations. What does it mean? It means that we have the Einstein tensor expanded linear order for H1, and then we set it to 0. This is what we did on Monday to derive the Regge-Wheeler and Zeeman equations. Okay. Now we are going to go to the next order. So we have some the linear variation of the Einstein tensor over H2. This is now is not going to be equal to 0, but is minus the second order variation for the quadratic part and perturbations of the Einstein tensor for H1. Okay. Now the idea is, as you can imagine, conceptually is essentially identical to the one that we followed Monday. We just, well, the idea is to first, let's say, fix a gauge, to remove some freedom associated with different variance, okay? And then we are going to, well, the idea is to introduce some master variables. Let's call them psi plus minus 2, where these 2 refers to the fact that we are at second order in perturbation theory. Monday we were calling these, well, these are essentially psi 1 would correspond to the original Regge-Wheeler and Zeeman variables, if you want. Okay, and then the idea is the next step is to solve for psi 2. So we want to find a solution for psi plus minus 2. And extract what are called the quadratic quasi-normal modes. Usually, sometimes are called quadratic quasi-normal modes. Okay. And eventually re-express these in terms of, for instance, TT gauge fields, which are the ones that are linked to the observables. Okay. This is more or less the logic. So, of course, remember that the equation that we wrote with the Regge-Wheeler variables was something like this. Equals 0 for psi 1. Now we are going to have a similar equation. We expect but now it's not equal to 0, but it's equal to some source. Okay? Because of this part. Okay? This is pretty obvious. Okay? This part, the left-hand side, is identical to the operator of the Regge-Wheeler and Zeeman equations, of course. And this part is constructed, of course, is second order in the fields, and is constructed by combining 2 first-order modes. Okay, this already tells us something important, that the frequencies of second order are essentially the sum of first-order frequencies. So you can have this for instance, or you can have that this is equal to m2. Otherwise it seems to be squared. So L1, M1, N1 minus L2, M2, N2 star. Okay? These are the 2 possibilities. In other words, you combine frequencies, first order frequencies. You can put the 1 if you want to stress that these are first order frequencies, and you can get a second order frequency, which is just the sum of the original frequencies.
Sorry, also in your equation there should be omega omega 1
Yes.
square and omega 2 square. Okay.
And of course, as you can imagine, so this follows from the fact that at each order in perturbation theory, let's say a J order, the real field is just the real part of some field J, which is complex. So when you plug these into the equations, you get, of course, that G mu 1 H complex 1 is equal to 0, but at second order, you get 2 is equal to minus d mu 2 1 half H 1 plus H complex conjugate H. Anyway, this is pretty obvious, but these are so this is just to say that this is why you get these two modes here. Okay, and the negative sign here can be also thought of as being coming from a sort of a mirror mode. Mirror mode means simply that it has the frequency minus omega star. If you want, you can think of this guy as being some mirror mode. So you take the complex conjugate and you put an omega star. So remember that we mentioned last time that the linear quasi-normal modes are isospectral. So the odd and the even part of the spectrum are the same. So they are degenerate and they have the same spectrum of frequencies. Now you expect that at second order this is also true in the sense that you are combining all possible frequencies, first order frequencies, so the outcomes, of course, the same set of second order frequencies. So you expect that isospectrality will hold true also at second order. Yeah.
Does this also imply spectrality beyond second order?
I guess so.
These are just relation?
Yes. Yeah, I guess in perturbation theory, this is the outcome. Yeah. So, okay, so then the idea is, of course, well, we have this equation and then we have to solve it. And you can use, if you want, the methods that I mentioned before, combined with the standard Green's functions method. So this is pretty standard exercise. Of course, it's very highly non-trivial in the sense that the source is can be complicated. So it has a lot of information, and then you have to do some effort. But conceptually, is straightforward. The way you proceed. In fact, the whole point is to find the inhomogeneous solution to this equation. So, of course, there are, so in this sense, the problem is conceptually identical to the one that we already discussed, but there are some differences. So let me stress that as opposed to linear modes, as we briefly discussed during the break, so linear modes, the frequencies are completely fixed by the properties of the object. So for a black hole, they are fixed completely in terms of the mass and the spin of the black hole. But the amplitude is a free parameter that will follow from the initial conditions. Okay. Here, instead, the amplitude is fixed. Amplitudes of psi plus minus 2 is fixed. Fixed in terms of first order quasi-normal modes. And for obvious reason, because you're solving a homogeneous equation, okay? And that's the whole point, in the sense that the frequencies they are already determined here. So the whole problem is to fix, is to find the amplitudes. And then there is another difference that one has to be careful. So you want to be careful in defining some second order master variable. So this requires perhaps or master scalar, so requires some attention in the literature. There is some discussion what is about the master scalar. In other words, if you use the standard assets that we used for the Regge-Wheeler and Zeredi variables, you run into some potential trouble in the sense that you see some divergences at infinities, which in the end are completely immaterial, but they can make the numerical analysis or the solution a little bit tricky if you want. So there is some discussion in the literature which kind of master variable it's you might want to choose to find these corrections. And of course, let me say that recently there has been some interest in this topic because there have been some numerical simulations that claimed to be able to confidently identify these second order modes in the simulations. So the idea is that eventually when one will be able to perform a more precision analysis, if you want, of the ring downs, then you might want to take these nonlinear modes into account. So as an example, for instance, in a recent work, let me just give you some numbers. If I have, do I have the numbers? Yes. So if we call with R the ratio, let's say, between in the TT gauge of the amplitude of this second order mode with L, M, and some N, I will tell you what this is. L1, M1, 1. So these have been computed in various references. I'm following one specifically, which I can tell you later. Well, this N is the overtone, and M bar is the mirror mode. It can be plus minus depending on whether it's the standard mode or the mirror mode. So I think in the paper by Luca Santoni, Enrico Trincherini, and others, they find that this R is something like this, 0.1, 5, etc. 4, 0.0, 6, 8. For this mode 2, 0 plus, combined with same, going into, if I'm not wrong, 4, 4. So this is just to say that, so this is just an example. The message is that you can solve the equation, you can compute the amplitude of these second order modes just by solving the homogeneous equation. You can compute the ratio, and the ratio will be some number, of course. The relative ratio with the first order modes. And you can find some result. They did it using some semi-analytic methods, and they find some. So these results seem to be in agreement with numerical simulation. Of course, as I said, it's not the only work. There are works where these corrections are, this ratio has been. And of course, I didn't tell you, but this L, of course, as you can imagine, satisfies the standard inequalities. Okay. So these are just standard angular momentum rules when you try to when you combine the two first order modes on the right hand side. There are questions about this? Because in fact, I think that this is a good time to stop, to close the topic at least. So I would, we can have maybe some time to answer questions, or if from today or from Monday, if I went a bit too fast, yes.
Sorry, I don't understand why you compare A2 with a product of 2A1. I mean, usually you would like to compare one amplitude with one amplitude. H is linear in the H mu nu is linear in the amplitudes.
Very good. Yes, H mu nu. So H mu nu 2 is a linear in the amplitude A2. But so if you think of this equation for a second, so the right hand side is quadratic in H1, so the linear modes. So the right hand side is quadratic in first order. And now, see, if you want a number, you have to divide by this square.
Yeah, but what I was saying is that at the end, the full H mu nu is equal H1 plus
yes,
H2.
you can factor out, but you can factor out an H1 squared.
Okay.
Because that is not very, so that is fixed, as we said, by initial conditions. So this level we don't have a control, but we can extract. So GR will tell us that the ratio, the relative ratio, is fully fixed by the form of the source. So this is a property of GR, and this does not depend on initial conditions.
So this ratio will depend on what? On the masses of the initial.
Yes, will depend. Well, no, will depend on the properties of the core. Yes, yes, fully fixed by the background solution. Of course, if you go at some point, the whole perturbation theory break down. So this approach, you have to resum it and to rely on some numerical methods. But there is a sense in which this is still perturbation theory is still good, and this provides some correction. Of course, the question is whether these are. So if you compare, so nonlinear correction of the dominant mode with the linear dominant mode, you expect this to be small, but you can ask the question to what extent this maybe is large compared to overtones.
Just R equal 0.15 means that we should take into account the second order, or means that we can drop it? Well,
now, right now, you can, I guess you can drop it, but I think the idea is that as we go on in precision, and so there is more events with new experiments, so on. I guess the idea is that this might be you might be able to see it. Of course, you can debate whether what is the best way of testing GR, but in principle, this effect can be computed, and in numerical simulations, at least there are analyses that claim that this can be extracted from numerical simulations. And in principle, this is a robust property of the theory. In other words, this ratio is fully dictated by GR in this case.
In practice, from the data, how do you measure these kind of things? Do you, I don't know, take a Fourier transform of the signal to find the frequencies corresponding to these normal modes, or do some more complicated fitting procedure? I don't know.
But you're asking these papers how they extracted these modes, these second order modes?
Or even the linear one, the first order one?
Well, so at the most trivial level, as a pedestrian, what you do is to say, well, we have some sines and cosines with some frequencies. Let's try to fit with
It's free. You take the amplitude 3 and you get the best fit.
Conceptually, this is what you do. So in practice, it's slightly, I guess, more complicated, but conceptually, this is the idea.
And when you said, I think, like we know which are the most important modes, like L2, you said.
Yes.
This is because of numerical simulations which go from the inspiral to the merger and the numerical relativity.
Yes, I
computations.
think that's true. Yes. I think from numerical simulation, this is what people usually claim. Yes.
If I would like to study link down of black holes in ADS, how much would
Yes. Okay.
how much would I mean, I guess the only change is in boundary conditions at infinity, but how would they look like more or less, or how much it would change the whole thing?
No, I don't think so. I'm trying to remember because I was reading something recently. So I don't know, but conceptually, I'd say that there is the idea is essentially the same. As you said, I'm just imposing the field some different boundary condition at the ADS boundary. But you're asking about what are these frequencies? How are they different compared to these ones? That's your question.
Yeah, or since I mean, this may be an A, but I think of ADS as some finite box, and so how should I think of these boundary conditions at the edge of this box? Or
well, you will impose it. We can check what people have done. Now I don't exactly remember, so I don't want to say something that's wrong. But yeah, but it's precisely what you said. You will impose some the field is zero at the boundary. Then it's like some finite box, and you can compute the solution. But we can check. Yeah.
I big things, but at some point, no, because the frequencies are complex, so you said so you have a mod outgoing so far from the black hole, well, the outgoing mod which is decaying in time and growing in space. So of course, so I assume this. So it means it doesn't make sense up to infinite radius. So it means this expression or this result is valid only up to some radius, up to some distance from black hole, which maybe just the speed of light times the times in the merging, or I don't know, or something else.
Well, no, yeah, as we said before, this might seem not a very nice picture because, as you're saying, if I put some perturbation far away from the black hole, there will be a huge effect on the spectrum. So the spectrum will be dramatically different. But this is in some sense, as we said, an artifact of how the problem is solved. So in frequency space, if instead you use some to work in do some time evolution, if you want, there is a sense in which the perturbation is the effect of the perturbation is retarded. So I think so. If you think of an isolated black hole, the picture is perfectly fine. You can ask the question, what happens now if I put some perturbation? Because in fact, in reality, there will be some other stuff around. There can be some environment, and so on. But if you take a single black hole, the frequency space analysis, I would say it's good enough. But the problem is so, as we said before, so if you think of the problem, so there is a sense in which working with the Green's function, you can make sense also of the case in which you have a small perturbation and so on. So the fact that it grows at infinity is not really, I would say, I don't think it's really an issue. It's formally, so from a mathematical point of view, is not very nice, but in practice, I think it's fine. or at least there is a sense in which this is okay.
A general question. When you use this perturbative framework, the position of the horizon is fixed. It does not vibrate anymore. That does not change. Or
Yeah, yes, and
no, my question is when they merge, you expect that the horizon is, well, I don't know how do you describe them, but the horizon moves, no?
yes. So of course, so it's not a yeah, but let me say that the picture of perturbation theory is not very robust in that case. So everything is fully nonlinear. So of course the solution is it's going to be order one different from the one that we wrote. So yeah, of course everything will be very distorted, and then yeah, we will have a system which is a highly order one different, let's say, from the standard solution of an isolated black hole. So in that case, you cannot apply this logic in which you say that well, there's a background with fixed horizon and perturbation stop.
Otherwise said, how do you know that when you see this what we call a ring down? How do we know that the horizon is still not is fixed, frozen, and not vibrating? It's
Well,
conjecture, I mean.
What do you mean? So,
Or it's negligible, I don't know.
well, I wouldn't put too much emphasis on the horizon in the sense that here, as we said, the effect of quasi-normal modes comes from, let's say, as we said, predominantly from the maximum of the potential, from the light ring, which is not exactly the horizon. But still, the way the problem is phrased is that, well, I start from some background solution, I study perturbations. So at the linear order, you have this potential. Of course, at the next order, the effect will be modified because we are now superimposing some, you have some H2 correction. And of course, the original solution, they will receive correction, so on and so on. So in this sense, in this perturbative scheme, this is how it works. Yeah, I don't know if this answers your question, but I wouldn't put too much emphasis on the horizon at this level because these effects mostly rely on the properties of the potential around the light ring, let's say.
Somehow, the horizon fluctuates a bit, like you said. Somehow, it's like you're changing a bit the boundary condition near the black hole. But I guess it doesn't matter so much, maybe because you say you are far from the maximum of the potential. So even if you change a bit, you are going more or less to select the same wave function, which has to decay or to be purely going in this way.
Yeah, so you're talking about the second order modes that live on a metric which is perturbed. This is what you have in mind?
I don't know. I mean, just that if the horizon is not exactly is not completely regular. I mean, it's not.
Yeah, a second order. You're saying a second order. I see a black hole which
And just because you are after the merger, so it's
yeah, sure,
completely.
But everything is already taken into account here. So this is the fact of some sense of the source. Of course, the homogeneous equation is not particularly interesting in the sense that it gives the same solution as a linear order. So, but the homogeneous solution knows precisely about this fact, about that we are expanding not around an unperturbed background, but there are first order perturbations. And yeah.
So more questions? So okay, thanks, Luca.